Welcome to another lesson with me, Mr. Wong. Today we will be exploring a concept known as molar volume. Before we go on to molar volume and the different gas laws, we need to firstly go through some calculations to revise on our understanding of the combined gas laws. That's from Boyle's law, Charles' law, and Gay-Lussac's law. So these are the questions. Just pause here if you want to have a go yourself. I'll be trying it in a second. Alright, so if you read through the question carefully, we have a sample of gas at a pressure of 101 kilopascals at a volume of 2.5 liters at 100 degrees Celsius. And the question's asking you what would its volume be if we change that temperature to 0 degrees Celsius, but we left it the same pressure. Well, we know that to do any of these calculations related to temperature in chemistry, we need to firstly change the degrees Celsius to Kelvin, and to convert that, it is adding 273.15. That leads us to 373.15 Kelvin. And the 0 degrees Celsius would be 273.15 Kelvin. Pressure stays the same, and obviously this is not related to our question, so we don't have to worry about the value for the pressure. It's kind of like a red herring here. If you read through the question carefully, 2.15 liters, that is for V1, so that's our initial volume. 373, that is T1, that's our initial temperature, and then 273 Kelvin, that is T2, that's the temperature change we have here. So now that you've got all the components together, substitute it into your formula. And so as you can see, 2.5 there, 73 there, 273 there, and then we get an answer of 1.83002 liters for V2. If you then go back to reading through your question, you will notice that 2.5 liters is two significant figures. That's the lowest one in your question, so that's also why we rounded off to two significant figures for the question here. Next question, you're looking for the pressure, P2, and you have these values here. So you have the volume at 1.3 liters at a certain pressure and certain temperature, and then we're trying to look at what's the new pressure if the volume and temperature are now this. Now there's a couple of things you need to do. Firstly, again, you need to convert the temperature into Kelvin. So 80 degrees Celsius, if you add that on to the 273.15, that is equal to 353.15 Kelvin. 30 degrees here, if we change that around, that is 303.15 Kelvin. And then the last thing we have here is the milliliters. So in chemistry, volume is always measured in liters. So to convert from milliliters to liters, divide by 1000. So you can rewrite this as 0.5 liters, or sometimes I like to do it when I'm teaching physically, is write 510 times the power of -3 liters. 10 times the power of -3 is the same thing as saying divided by 1000. If I look through my question, everything on top here, 1.3, that's V1, pressure, that's P1, T1, and then this is V2, and this is T2. So written it all out, that's what you need to do when doing calculations, to write down all the components, and then you simply substitute it. Okay, and there we go with that, and you should get a value roughly to 225 kilopascals, just looking at the significant figures we used, 3 sig figs we have here. being used. If you have a look here, this should be corrected to KPA lowercase. That's just notations, so that's all we need to worry about. All right, and there you go. That's just how you do those two questions there. Moving on now, let's just recap quickly what we've done so far. We have talked about Gay-Lussac's law about temperature. We've looked at Boyle's law, Charles' law. We're now going to look at Avogadro's law. If you remember Avogadro, he was the guy who came up with the mole number, and so we're going to learn a little bit more about applying the mole to gases. So this is our lesson intention today. We are again looking at the mathematical relationships that exist for gas molecules, and we're going to try and look at how these quantities affect each other. Textbook reference is there if you need. All right, recapping the ideal gas laws. If you recall, if something is an ideal gas, it's in constant random motion. It does not attract or repel other gas particles. We're assuming they don't come into much contact with each other. If they do end up colliding, that collision is completely elastic, so no energy has been lost during collision. They've just been transferred over to each other. And we're saying that the amount of space they cover in some kind of container is negligible, so 0 volume they occupy. One of the properties of gas is diffusion. If you look at this video time lapse we have at the bottom right hand corner, you can see over a period of time this gas, which I assume potentially chlorine, it goes from an area of high concentration to low concentration, so it was rising upwards. Okay, so at the start of the video, if I can just quickly put that back, at the start of the video, all that gas is at the bottom where it's highly concentrated, and then what happens is all the gas will try to move to a location where there's not much chlorine gas concentration. So which direction does gas move? High concentration or lower concentration? It moves to the area of lower concentration. Okay? And so what can we say about diffusion? Well, diffusion is basically a property of gas, or water that is, where particles go from an area of high concentration to low concentration. This is the concept that you probably would cover a bit more in biology, but that's a property of gas. It's like saying, if you have that one annoying friend who sprays their deodorant in class, and all of a sudden everyone in the classroom smells it, that's an example of diffusion, because the little particles, the little gas particles from that deodorant, once that person sprays it, goes to all parts of the room where there is low concentration of that deodorant. So that's just a property of gas, and we've looked at other things related to gas laws. Remember, anything that's a scientific law is something that can be continuously observable. One of the things that's always observable, again, we're looking at Gay-Lussac here, and he came up with a law when combining different gas particles. So he did an experiment where he had hydrogen gas and chlorine, and he combined them together. And what he found, same thing he was doing with hydrogen and oxygen, he found gaseous water. What he found was whenever he mixed gases together, they kind of combine in whole number ratios. So what do we mean by whole number ratios? So he wasn't getting decimal points. So when he combined 1 volume of hydrogen and 1 volume of chlorine, he didn't get 1.5 volumes of hydrogen chloride. He got 2 volumes. So that's what we mean by whole number ratios. And the same idea, that's what he got for hydrogen and oxygen when making gaseous water. Okay, so under constant temperature and pressure, the volume of gas taking part in a chemical reaction shows simple whole number ratios. And this kind of is the fundamental part of when we talk about balancing chemical equations. Why do we do it in whole numbers? Because scientifically, experimentally, we see things combine in whole number ratios as well. That's why when you balance an equation, you need to use whole numbers. It'd be sort of cheating if you used fractions. And then we come through Avogadro's law. Like I said many times, Avogadro didn't actually do any experiments himself. Rather, he actually looked at other people's scientific data and he made some observations and, voila, became scientific law. So he looked at Gay-Lussac's experiment. He said hydrogen, oxygen, and then gaseous water. He made the point that not only do they combine whole number volume ratios, but these volumes are actually whole particles or whole molecules in motion. So 2 volumes of hydrogen in Gay-Lussac's interpretation. In Avogadro's interpretation, it's 2 molecules of hydrogen gas. Oxygen, 1 volume of oxygen is 1 molecule of oxygen gas, and then 2 gaseous volumes of water, you have 2 molecules of water. If you look at the equation, like I said, this is where the idea that you need to combine when you're balancing chemical equations, everything comes in whole number ratios as it just balances out that way. So that's essentially why we do whole number balancing chemical equations, because Avogadro's law and Gay-Lussac's observation shows that in nature, by nature, things combine in wholes or simple whole number ratios. So again, this only holds true when he was doing his experiment in the same temperature, pressure, equal volumes of different gases. So, if he was using 500 milliliters of hydrogen, he was using 500 milliliters of chlorine. Okay, that's also how we can ensure it's a valid experiment anyways. Next bit is we also know from that fact that hydrogen and oxygen are diatomic, so they come in pairs. We also know that water's formula was H2O, not OH, and obviously allowed for balancing chemical equations. This is really the main point of their observation. It's the fact that we can work out that balancing equations, you need to do it in whole number ratios. All right, so let's try and break this down into some questions. So what is Gay-Lussac's law of combining volumes? And then let's try and apply that knowledge to this equation here, okay? So what is the Gay-Lussac's law of combining volumes? So we're essentially saying gas substances will combine their volumes in whole number ratios if the temperature and the pressure of the system is constant. In other words, those systems are not changed, then the volumes will just combine nicely in whole number ratios. We have methane burning in oxygen, and this produces carbon dioxide and water. Okay, this should be liquid. My apologies, just a little error there. That should be a liquid. Okay, now back to the actual question. If we have methane and oxygen at the same temperature and pressure, again, this is just how the ideal gas laws work. The volume of carbon dioxide and water vapor produced by the combustion of 1.2 liters of methane in excess oxygen. So how much carbon dioxide and water do we get? Now let's look at it. Okay, let's look at the mole ratios. So we're looking at methane, we have carbon dioxide, we have oxygen. So if we're comparing simply between methane and carbon dioxide, it's a 1-to-1 mole ratio, which means the exact same amount of volume should be produced. So you would expect that carbon dioxide would also have 1.2 liters of production. And then because water is in a 1-to-2 mole ratio in favor of water over methane, simply just times the 1.2 liters onto water. So we set the ratio of methane and carbon dioxide is 1-to-1, water is 1-to-2. So methane, if you have 1.2 liters, you'll also produce 1.2 liters of carbon dioxide. And 1.2 liters of methane will produce 2.4 liters of water. Simply, I just compared the mole ratios. Okay, next question. We have the volume of gas produced by the combustion of 25 milliliters of methane. So let's again look at it. We have methane. 25 milliliters of methane would produce 25 milliliters of carbon dioxide. Same ratio. Mind you, this is assuming that oxygen is in excess. So we have lots and lots of oxygen to use anyways. So we don't factor in that. And so if we have 25 milliliters of methane, we have 50 milliliters of water. And so the total gas we produce, if you add the carbon dioxide and water volumes, is 75 liters. Right, so we talked about moles. We said moles is just a counting quantity. You have that really fancy number, and we talked about if it's with elements or compounds. What you see on the periodic table, let's say the mass of iron, that's the molar mass of iron. So out of 6.022 10 times 23 particles of iron, it's about 55.9 grams. Okay. And then we said the same thing for helium. Now, helium, for things like non-metals, helium is a gas, and so we did say that most gases, it's quite difficult to measure the mass. So we try and change it up, okay? So we're back to our counting tools. We're back to the mole. You know, chemists use this all the time to count the individual number of particles, compounds, molecules. And so we actually develop a new kind of term. We call this a molar volume. So we said that with gases, you have difficulty measuring the actual mass because you can't actually compress that gas together. So you're just trying to measure how much space it ends up taking up. And what we know, and that term we use to say that a mole of gas, we call it the molar volume. So it's the volume that 1 mole of that particular gas molecule can occupy. But do remember, volume does change with temperature and pressure. And so we actually have two calculations or two numbers for molar volume. One is the standard laboratory conditions. So when you're working in a lab, and that's 24.79 liters. So that's how much space a regular gas or 1 mole of gas would occupy in a lab condition. Standard temperature and pressure, 22.71 liters. And I'll go into a bit more detail what that kind of looks like. It's standard lab conditions, 24.79 liters. This is what it kind of looks like if you want to try and picture it. So 24.7 liters would be about 12.5 bricks. It would also equal to about 12 liters worth, or just above 12 liters worth of milk. So that's about the amount of space gas particles would occupy in standard lab conditions. So if we try and quantify, make a value out of this, or make an equation out of this, molar volume, Vm, okay, that's the number we were talking about, either the 24, so the molar volume, if it is standard lab conditions, is the 24.79 liters. And then if it's the standard temperature and pressure, that's the 22.74 liters. That's that number there. Okay. So we know that N is just the number of moles. V is the volume of gas you have. Okay. So standard lab conditions, it's when temperature is roughly 25 degrees Celsius, so 298 Kelvin, pressure 100 kilopascals, mole volume will be 24.79. And if it's the standard temperature and pressure, then the temperature would be at 273 Kelvin. Pressure stays the same. Volume is slightly lower. So that's the only difference between standard lab conditions and standard temperature and pressure conditions. It's only different by the temperature. All right, so if we try and apply what we know from the molar volume with these calculations here, the form is there on the side for you as an assistant. Have a go and I'll explain it in 2 seconds. So pause now. All right, so forgot to put my transitions on, but that's okay. So we said we have occupied, we have nitrogen gas, 2.4 moles of it occupying the space. So that's what N is. This is standard lab conditions. So we're looking at volume. So we're trying to find V. We know what the molar volume is at standard lab conditions. It's 24.79 liters. So substitute 0.24 and substitute 24.79. If I want to make V the subject, I times both sides by 24.79. That's just how it works with the equation. And I get this value here, which I get 5.9496. If I look at my equation, look at it carefully, I have 2 sig figs as the lowest one, so 5.9 liters. If we look at question 4, same idea here. Standard lab conditions again, so I substitute 24.79 straight away. I have 90 liters of oxygen gas, so this is 90 liters, and I am trying to find the number of moles. So in here, this is the value I get once I put it into my calculator. And again, reading through my question, 90 liters is the lowest significant figures of 2. So then I round things off to 2 significant figures. So 3.6 moles. And so there's a little interesting relationship between molar volume and molar mass, because obviously if you know what the molar volume is, you should be able to convert. So if you know what molar volume is, you can convert back to number of moles, N. If you know the number of moles, you should be able to work out the mass relationship and also the number of particles the gas may be occupying. So that's kind of how we kind of can backtrack on calculating the potential mass of the gas we're measuring by looking at the amount of space it covers to the amount of particles we predict there will be, and also how much mass that would be equivalent to. So let's try some calculations related to that. Okay, again, 2 seconds before I move over, so pause now. All right, so in this question, question 5, we are trying to look for mass. So M is the thing we want to know. We know the volume. Again, convert this into liters. So divide by 1000. We try combine it with 25 degrees Celsius, pressure of 100 kilopascals. So these conditions, that's the standard lab conditions, which means molar volume is about 24.79 liters. So you have volume, you have molar volume, substitute that in, that's the value I get. Okay, still trying to find mass, so no rounding offs yet. Okay, so knowing that my number of moles, carbon dioxide is what I'm trying to find. So I'm trying to find the mass over molar mass. Carbon dioxide, you can find that on your periodic table. Carbon dioxide's molar mass is about 12.01, and then individual oxygen atom is about 16, so times by 2. So I work that over to find the mass. That's the number of moles, that's the molar mass of carbon dioxide, and I get it round off to about 0.914 grams. Okay, straightforward enough. Some people might ask, temperature, that's 2 significant figures. Why didn't we round off to 2 significant figures? You usually, from my understanding, you only round off values that are involved in the question. So because the temperature wasn't actually involved in our calculation, we don't take that into account. Question 6, we have ethane. That's the mass. So we're actually working backwards now to what we did in question 5. So we know the mass, we know find the molar mass of ethane. So carbon is 12.01 times that by 2. Hydrogen 1.008 times 6. So we put those numbers in. That's what we have. 3.11, 30.068. We find the number of moles is equal to this value here. Again, we're not going to round anything off just because that will affect our overall numbers, and if it was in the HSC, you would be marked down if there was some slight rounding off issues. Okay, pressure 100 kilopascals, temperature 0 degrees Celsius. So this time it's not standard lab conditions, this is standard temperature and pressure. And we know that when that happens, we use this number, 22.71 liters. So we put that in. So our number of moles times the molar volume, and this is what we get. Again, round it off to 3 sig figs because we don't take into account temperature. So 2.35 liters. And that's essentially how you do these calculations from mass to volume to mass. Obviously, we don't have questions related to particle numbers, but obviously you can search that up as well. And so that's kind of the summary of the gas laws. We've basically covered everything in module 2 now. We covered the last inquiry question. We talked about Gay-Lussac's law, how constant temperature and pressure leads to what, Avogadro's law, and then obviously molar volume is how much space a gas or 1 mole of gas can occupy at a given time, assuming that we know the temperature and pressure. And that's it for today. Thank you for joining the lesson. I'm Mr. Wong. Have a good day and take care.